Beyond the 3D geometry, a modern building information model functions as a complex relational database, governing the entire lifecycle of a facility. These models organize tens of thousands of distinct standard components, each carrying its own set of precise specifications. As the project moves from initial design through procurement, the data embedded in these components accumulates. By the time the facility reaches the handover phase, the operations and maintenance teams require highly specific, queryable information extracted directly from the model. A digital model's operational utility depends on its ability to accurately deliver this facility data at handover, outlasting the importance of its geometric precision. Contractually, project teams must deliver an Asset Information Model, or AIM, to the facility owner. This diagram shows the mandated grid of asset attributes. It demands specific data points for every component, such as fire ratings, warranty dates, and serial numbers. This applies to every maintainable asset, creating millions of data entries managed simultaneously. Injecting this volume of information into a model without a strict structural taxonomy creates database bloat and corrupts the entire system. The core architecture of building information modeling handles this load by bifurcating all data into two distinct categories: type parameters and instance parameters. Mastering the absolute division between type and instance parameters is the mandatory first step for IFC plus SG compliance and for generating a functional digital twin. Modern design for manufacturing and assembly relies on standard parametric components as the primary building blocks of a model. This UI properties panel represents the data attached to a standard commercial fire door. We call the first category of data type parameters. This is the data that dictates the universal shared characteristics of this specific asset class. Look at the supply chain properties. The manufacturer name and the model number are hard-coded into this panel. The performance specifications, like the 2-hour fire rating and the thermal transmittance, or U value, are also located here. These inherent properties exist completely independent of where the door is actually placed within the physical building. Type parameters define what the object is. They establish a master template for the rest of the model to reference. We cannot deploy this standard component across a large-scale project. Here is how the geometry behaves when we multiply that single fire door into 50 identical doors scattered across different floors. Watch what happens when a user updates a single type parameter, changing the fire rating from 1 hour to 2 hours. All 50 doors across the entire building instantly reflect this new data simultaneously. This centralized global update capability is the primary efficiency driver in virtual design and construction. But this efficiency carries a risk. If a user accidentally inputs location-specific data into a universal type parameter, they overwrite the data for every single door in the project, ruining the dataset. Because type data is universally shared, it must never contain location-specific or installation-specific information. To handle installation data, we have to isolate a single physical occurrence of the asset. This new panel represents instance parameters, the unique data defining one specific item in space and time. This is where we record the specific spatial data required, the exact XYZ location coordinates, and the story number, such as level 3. Operations and maintenance teams also require temporal and warranty data that is strictly tied to physical installation, so we populate the instance panel with the precise installation date and the warranty end date. Finally, to track the asset over its lifespan, it requires unique identification. We assign a unique asset identifier tag and record the manufacturer's exact serial number right here. Modifying an instance parameter isolated to this one door has zero effect on the other 49 doors in the building. Type parameters define the theory of the design. Instance parameters define where and how the object exists in physical reality. This exact data taxonomy dictates how models must be prepared for regulatory submission. The CoreNet AX platform operates on strict IFC plus SG parameter mapping rules. This interface shows data fields being mapped from the native BIM software to IFC property sets, utilizing the IFC data extractor and shared parameters tools prior to export. The validation process strictly checks for the correct division between type and instance parameters. If a user incorrectly maps a unique installation date to a type property set, the system triggers a validation failure. The database physically cannot assign a single calendar date to a universal asset class. The logic breaks. Remapping the installation date to an instance property set restores the logic, resulting in a green validation pass. Automated model checking relies entirely on this logical bifurcation. Failing to respect the taxonomy breaks the IFC export. For BIM coordinators executing these models, there is a clear operational rule. This matrix provides a technical framework for differentiating these two data types. If the data is true while the item is sitting in a manufacturer's catalog or a warehouse, information like brand, model, and fire rating, it is a type parameter. If the data only becomes true once the item is physically bolted into the building, like the serial number and the installation date, it is an instance parameter. Maintaining this clean data architecture ensures multidisciplinary coordination succeeds on site. It guarantees that contractual deliverables under the BIM particular conditions are met efficiently, without manual rework. Ultimately, the facility owner receives an uncorrupted, clearable digital twin ready for immediate operations. Respecting the rigid taxonomy of type versus instance is the foundational step in transforming an abstract 3D model into a functional, lifecycle-ready asset.